Hello, my name is Lucy Wright, and I'm technical support for the photoelectric sensors with Pepperl+Fuchs. Today we will talk about the technologies of diffuse mode sensors. There are two main detection or measurement technologies, triangulation and time of flight. Respectively, triangulation operates with such definitions as dual pixel and multi-pixel technology, based on what is the receiving element. Does it consist out of 2 pixels for near and far field, or multiple pixels arranged in an array? When the receiver consists only out of one element or pixel, we speak about single pixel technology, which is used in the energetic diffuse sensors, but not triangulation. More about it on the further slides. Both energetic and triangulation methods in the diffuse mode sensors are similar in that the object reflects the light back to the sensor to be evaluated. But for energetic diffuse mode, this is where the evaluation stops. If the light is returned on the photodiode above some preset voltage or current threshold, then an object is detected. It detects proximity, but is never consistent about it over color changes. Therefore, the accuracy about the real position of an object is low. It determines the presence of an object, not its position. If in the background there are more reflective objects than the actual target, then the background objects will be detected, but not the actual target. So this is energy-dependent system. The amount of light energy coming back from the target depends on the reflective index of the material. Please look at the animation to see how different color of the target influences the amount of light energy coming back. And one more time. Here you could see the most popular energetic diffuse sensors in our portfolio. Those are sensors with SPT single pixel technology: GLV18, RL31, RL61, VT18, ML17, OBT series, GLK18, OBD, and OC300. When you go to our homepage www.Pepperl+Fuchs.com and go to Product Search, Photoelectric Sensors, Diffuse Mode Sensors, and choose our search filter and choose under Special the option Energetic, you will be able to find all energetic diffuse mode sensors. Based on the triangulation principle, the sensors of Pepperl+Fuchs are all either background suppression or background evaluation or analysis. Today, we will be looking particularly at the background suppression sensors. They detect objects up to a defined distance but not beyond. The light from the sensor's emitter is reflected by an object to the sensor's two-segment receiver based on the distance of the object. Remember, we were talking about dual pixel receiver. Depending on that triangulation angle, the object is either detected or suppressed based on which receiver segment sees more reflected light. This way, background like machine panels, conveyors, and sidewalls can be correctly ignored, and materials and products with varying colors and printing are seen at a consistent distance with no adjustment needed. Let's look at the dual pixel technology, which provides 2 pixels, shorter pixel far diode and longer pixel near diode, and compare with the single pixel technology SPT, where only one single pixel is available. There where the light spot falls, there the current will be created. Detection happens based on the position of the light spot, not on energy. Action range of the background suppression sensors can only be adjusted mechanically. The most common adjustment methods are adjustment of a position of a lens, mirror, receiver, or both lens and receiver module. Let's look at the benefit of a triangulation sensor. But first we need to understand some geometric relationships. There are a few variables in the system which we can define in relation to the optical emitter and receiver axis. X is the distance to the object. Generally, that is what we would like to know where the object is. H is the emitter-receiver separation distance, sometimes also called baseline. F is the back focal length according to the lens and optical design. P is the position of the light spot in reference to the receiver optical axis. H and X are building one right triangle, and T and F are building another right triangle. Now we can apply some basic similar triangle theorems and determine the relationship between the main variables in a geometric-based system. This is the relationship in our equation number 1. What is more interesting to show, however, is what defines the light spot P. We see that the light spot position is inversely proportional to the object distance. This means when the distance is very small, the light spot is high up on the receiver. When the object is far, the spot moves towards the bottom. Now let's look when the sensor turns on. When the light spot falls equally on the near and far diode, or completely on the near diode. But the sensor turns off when the light spot falls on the far field diode. Important is to know that with this dual pixel technology, only one switching point is possible. Here's another example to show the phenomenon we just discussed. Remember, the triangulation sensors really operate by detecting the light spot displacement. With other words, tracking the light spot walk. The light spot will literally walk on the receiver as the object walks back and forth in front of the sensor. There is the PCBA from the inside of the sensor, the near and far receivers, the emitter. On the video, the black backing is the same PCBA shown on the right. Then come receivers, then the emitter. The little lamp is the light being reflected from the object. The white spot represents the reflected light spot as it walks across the near and far receivers. Let's watch the light spot walk. And now let's watch the movement of the light spot as the object travels from near to far and back. Most photoelectric sensors use the dual pixel technology method because it is more economical and less complicated in terms of software and electronics. The disadvantage is, though, it requires mechanical settings to adjust the range, so no settings are possible with software, for example through the IO-Link interface. Here you can see which products we have with dual pixel technology. The sensor series OPT in different housings, ML7 ML100, GLV18, and RL28. As you see, OBT has only one fixed range possible, and in other series we need to either adjust the position of the lens or mirror to be able to adjust the range. Here is an example to show that it matters if the sensor detects objects in the background. Bottle cap error proofing. Normal condition is detection occurs when cap lid is present. Error condition is no detection, which indicates that the bottle cap is damaged or missing. On the other side, the sensor is able to easily detect objects in the foreground, near zone, and will not detect the machine panel in the background, far zone. We talked about dual pixel technology and basic triangulation. The basic triangulation is about detecting the proximity of object, whereas advanced triangulation is about measuring the true object distance. Sometimes a binary on and off signal is all that is needed in the application, and therefore a background suppression sensor with dual pixel technology would be a good option. But there are times when you want to know the exact position of the object. That is where the advanced types are needed. You remember we were discussing the light spot lock. Let's look at common light spot tracking components found inside the sensors. The first common type is the lateral effect position sensing devices, PSD. It is an elongated element for capturing photons along its continuous surface. The photoelectric effect causes current to flow as light strikes the sensing area with output currents proportional to the proximity between the terminal and the light centroid. The PSD element is predecessor to the multi-pixel technology MPT. The MPT technology is a large number of individual photodiodes pixels placed into a one-dimensional array. Among Pepperl+Fuchs products, there are R100 series which use MPT technology. The same idea of the far and near fields applies, but is represented by multiple individual photodiodes, pixels. The multi-pixel technology MPT was developed by Pepperl+Fuchs. This technology makes it possible to provide multiple operating modes. The position of the light spot along the whole MPT is known. Therefore, it is possible to set a switch point via software and even set multiple switching points. The sensors based on MPT technology provide multiple benefits, such as color-independent object detection or smallest black-to-white difference, interference-free distance measurement. The sensors are easily adjustable via I/O link. For example, detection range can be adjusted electronically, not mechanically anymore. Within one the same sensor, there are possible multiple switch points and windows. Also several operating modes selectable via I/O link. That is a big cost-saving factor. With this technology, there are background suppression and background evaluation sensors of the series OQT with multiple switch points and OMT with measured values. Let's look at the graphic differences in the detection with DPT versus MPT technology. DPT detects position with a threshold, whereas MPT evaluates the topmost position of the curve, which corresponds to the center of gravity of the light spot. DPT sensors are not suitable for remote parameterization because only mechanical and electronic adjustment is possible. They also have reduced detection range, since the light spot must always lie on the transition between near-far field element of the receiver. The black and white difference principle is not always avoidable. MPT offers the opposite to the DPT. It is ideal for remote parameterization, longer detection range, and there is no black and white difference. What is the limit of possibilities for MPT technology? Let's look at the next pictures. First example, A miniature sensor with a 25 mm height. This family has a background suppression version with maximum sensing range of 80 mm, which is approximately 3 inches. We do not offer this family with a measurement output. Next, a little larger family of 38 mm in height, and the background suppression type maxes out at 350 mm range, approximately 13 inches. And we offer an advanced measurement type which maxes out at 200 mm, 8 inch. Again, a little larger size, and we achieve a range of 650 mm, about 2 feet for the background suppression type, or 600 mm, about 2 feet for the measurement type. Last one, bigger housing, and now we have about 2 meters or 6.5 feet range. I think the message is becoming clear now. To achieve larger sensing range, the emitter-receiver separation distance has to become larger, and thus the housing size does as well. At some point, though, continuing to increase the housing size becomes impractical. Multi-pixel technology enables micrometer-accurate distance measurement, detecting even miniature product features and the slightest position deviation, like verifying small features present in assembly items like shown on this slide. This application requires checks to ensure that the bottles are properly sealed. If the caps are not completely sealed, the bottles are removed. After seeing the limits of the multi-pixel technology, the next step would be to reach out to a different way of detection and evaluation of the signal without making the housing even bigger to work with longer distances, and this is the time-of-flight. The time-of-flight technology is nothing new for us. We have seen it with radio waves, sound waves, and now we see it with light waves. The time of flight is being measured through direct time method or phase shift. Some manufacturers are going the path with phase comparison, but we choose the direct time method. To differentiate ourselves in this regard, we use the term PRT, pulse ranging technology, as a replacement for time of flight. How does it work? The light is emitted, the clock records it, then the light comes back at the receiving element, and the clock measures the time. Knowing the speed of light and the elapsed time, we can calculate the distance. Where are the challenges with this technology? When we know the speed of light and operate with such time units like nano or picoseconds, then we reach the limits in achieving certain resolution values. And why? Because the modern C-based CPU clock speeds which are available right now are up to 3 and 4 GHz for conventional CPUs and 8 to 9 GHz for nitrogen-cooled CPUs. There are general principles of pulse ranging technology. High energy and short duration pulse emitted. Time of flight of pulse is determined, and distance can be calculated based on a quotient shown. There are a few drawbacks of the direct time method. There is limited availability of different types of electronic chips like ASIC or system on chip, and it can be very expensive and difficult to implement into 3D cameras. The benefits of direct time method prevail though. This is good accuracy across the entire range, ambient light and crosstalk immunity, so it is the best combination for both long range and high precision. It is being used in 2D, 3D Lidar scanners for navigation and mapping of autonomous vehicles. Here's the example just of some sensor series based on the time of flight or pulse ranging technology. Our Lidar sensors R2000 with digital output and raw data output, R2100 and R2300. The distance sensors VDM100 and VDM28. Both multi-pixel technology and pulse ranging technology based sensors offer additional functions via IO-Link interface, Within one and the same sensor, it is possible to set up multiple outputs, background suppression, evaluation, window mode, and hysteresis. Thank you for watching this video. My name is Lucy Wright, and if you have any questions, please reach out to me under the following contact information.